Hello, everybody. Thank you for joining me at this talk. My name is Xiaochuan Yang. I am a research associate at the University of Bath. Today, I'm going to talk about the number of components of random geometric graphs. This is ongoing work joint with Matthew Penrose at Bath. Okay, so let me start with a small introduction about geometric graphs. Geometric graphs is a graph model, which is very simple to define. We need to specify two things. First is the set of vertices, which is given by a subset of Rd, where D is the dimension larger than or equal to 2. Second thing we need to specify is the connection, the radius of connection R, which is a positive constant. 2 points in the set of vertices is connected if and only if they are at distance less than or equal to R. There are plenty of applications in science and technology of geometric graphs. For instance, in telecommunication, points represents the location of base stations, and R has the interpretation of the range of coverage of the base stations. In machine learning, many graph-based clustering algorithms and some statistical inference method in identifying the topology of data, they require geometric graphs as a building block. So today, the main concern is the number of components of random geometric graph. That is when the points are sampled uniformly, randomly, in a certain subset of Rd. So before diving into the mathematical theory of this topic, let me first give a to show you some simulations. So here I'm going to fix the number of points, 1,000 points in the plane, and I'm going to vary the value of R and to see how many components are there. In the beginning, when R is very small, 0.01 in this case, they are very, the graph is very disconnected, right? There are many components. As I increase the value of R, we see less and less components until we reach to a point where everything is connected and the number of components is equal to 1. So we kind of see that the number of components, this problem, depends very much on the choice of R and N. So, so this can be put in into a more rigorous term. So we are going to identify different regimes according to this crucial parameter that I call lambda n. It is defined to be theta times n times r to the d, where theta is the volume of a d-dimensional ball, and n is the number of points, r is the radius of connection. Okay, so we consider points sampled uniformly randomly from a set A, and there are n of them. So the number of components kn would behave differently according to the limiting behavior of lambda n. So if lambda n goes to infinity, if lambda n goes to a finite constant, right, lambda, which could be 0, in this case, it is shown in Matthew's book that the number of components divided by the number of points converges to a positive constant. And this constant is equal to 1 if this lambda, this small lambda value is equal to 0. So this corresponds more or less to the first figure in the simulation. Well, when lambda n goes to infinity as the log n rate, so this is very precise here. So if you have, there exists actually two constants, C1, C2, such that if lambda n grows to infinity at this rate, where beta is a fixed constant, then one can show that kn without normalization minus 1 goes to a Poisson random variable with finite parameter, and this parameter depends on beta. So In this regime, eventually the number of components is of constant order. So sometimes this regime is referred to as the connectivity regime. So if you are more interested in this regime, then you are invited to watch Matthew's talk about this connectivity and coverage in stochastic geometry. You might have noticed that there are some leftover values. So what if lambda n goes to infinity, but at a lower rate compared to log n? And this is precisely the main concern of this talk. And in the abstract, I refer to this regime as the intermediate regime. So we assume 1 occurs and consider the number of components kn. In this case, not much is known actually. So there is a very nice result of Ganison in a few years back. He considered dimension 2, and the points are sampled uniformly from the square, 2-dimensional square. So in this regime, he showed that there exists a non-specified constant c such that the kn over n, the ratio, the proportion number, decays exponentially in lambda n. Recall that this is exactly lambda n when d is equal to 2. So our goal in this work is threefold. So first thing, we would like to identify this exponent in the exponential function. So the second goal is to have a general statement for a general set A in any dimension. And this could be of interest in, for instance, in topological data analysis, where the data points are sampled from a submanifold of RD. And third, we would like to have a quantitative fluctuation result in the sense of having a asymptotic distribution for Kn with some rate of convergence. And we will achieve these goals with the theorem. Here we consider dimension 2 or higher, and theta, recall, that is the volume of d-dimensional ball, and we consider a random geometric graph with n uniform points uniformly sampled from this set A and radius r, satisfying the regime, this intermediate regime 1. Then assuming very mild conditions on the boundary of A, we can show that indeed, so kn over n decays exponentially in theta and r to the d. So we have this specified value which is equal to theta, the exponential decay. We show more than this. We have this concentration bound and also a central limit theorem for a standardized version of Kn in the Wasserstein distance, and the error bound is very explicit. Okay, so the rest of the talk, so the last slides actually, will be devoted to the high-level ideas in the proof. So the key equation is this boxed equation. It says that Kn is equal to the number of singletons plus noise. Okay, so what is this noise? Right? Of course, we can always write the number of components as the number of singletons in the graph plus the number of components of order 2, 3, 4, and so on. So this equation basically says that all the non-singleton components are negligible compared to the number of singletons in this regime. So to be more precise, the main body of the paper is devoted to show the following two relations. The first is to say that the expected value of Kn is asymptotically equivalent to the number of singleton, and the variance of that satisfy analogous relation. So these 2 and 3 are really the crucial step, the crucial computation in the paper. So this can be done by some percolation arguments. So now I can tell you where this theta is coming from. So first, we can Poissonize the problem by replacing this ID independent, ID uniform points by a Poisson point process with intensity n times the uniform measure on the set A. For this graph, for this geometric graph with Poisson input, we can actually calculate exactly the number of singletons. So the number of singletons is asymptotically n the number of points times the probability that a particular point is singleton. And that corresponds to the probability that a Poisson random variable is equal to 0. And the parameter of this Poisson random variable is precisely n theta r to the d. So once we have this, we replace it back in equation 2, applying a Zoom inequality, we conclude with the concentration band. For the central limit theorem, it's the same idea. So we can first find a central limit theorem for the number of singletons by, for instance, Stein's method. Once we have that, using the estimate 3, the variance estimate, we can ignore basically the contribution from non-singleton components and derive a central limit theorem for Kn as well. Okay, so we are almost finished with the proof. So if you're interested, please check my website for updates of this paper. And thank you for attending this talk. I wish everybody very good time during the conference.